It's not supposed to do that.
This is the body from the water pump on the V65 Sabre. Now I removed the water pump using the traditional methods. Here is the main bearing assembly shaft, and she's pretty much scrap, as you can see. I'm really glad I took this out because I wasn't originally going to do that. So she's just tore up. I mean, just completely wore out. The mechanical seal obviously failed over time, and you got water inside the bearing. All right, so and here's the mechanical seal itself. You can see the back side of it. So here's the impeller, and she's in okay shape, no problem. A little bit of pitting down inside there where the other half of the mechanical seal would go. That is not anything out of the ordinary from what I've seen on these. Typically, that's about what you see. It was pretty hard getting this off the shaft using, again, the typical methods that you do from the kit that I get from AZV65. This is all done, so this one's all ready to go. The whole problem resides right here in the body. This is the bore we're talking about. This right here is the bore that the mechanical seal gets pressed into. Now, if you look really carefully in this bore, I know it's not the easiest thing to show you. There is some significant pitting, like right here. It's all over this bore. That's a pretty good shot of it, right next to that little blue dot. This bore is absolutely smoked. It is really pitted in most of it. And you got another big one right there. There's another one you can see really clearly, I think. Right about there. That is the weep hole you see right there in the bottom. So there's some significant pitting in this bore. The new seal comes with like a ring of Loctite. You know, that Loctite that's like pre-applied. So when you push it in, it gets activated from the friction and then seals this off. It's kind of a sealing mechanism. But it is a pretty good press fit to get the seal inside here. But there's no way in hell just that is going to seal this off with all that corrosion and pitting. And just for perspective purposes, I'll pick up the old one here and I'll show you how that goes. This would go this way and pressed in. I would like to save this water pump housing, but I'm not sure that I can. I'm thinking we could bore this out and put some sort of a bush in there with Loctite 638, and then we'll let it dry overnight and then come back in and bore this out to the proper size. This is very thin. There's not a whole lot of material here. If this was thicker, it would be a lot better, of course, because the difference between this size and that bore size is quite substantial, so we wouldn't have to worry about necessarily cutting into where the damn thing is, you know, cast together. But we do have to worry about this right here. I don't know if we're going to be able to do it. This is, the thickness of this is 110 thousandths. It looks a lot thinner than it actually is because of that chamfer on here, which is important for putting the other seal in, you know, the new seal. We have to measure this first. That's the other real challenge we have here, because there's not a whole lot of good bore left to measure. We got to get a really good measurement on what the nominal is on this. We can bore it out, let's say 30 on a side, a total of 60. And 60 thou should be enough of a remaining bush, because we would make the bush a lot thicker. We'd probably make the bush about the thickness of that inside bore down inside there, this one here. We'll make a note as to how deep to go on that shoulder. We can actually cut into that shoulder a little bit, because it is kind of chewed up as well. That shoulder does nothing as far as registering the seal. The seal has its own register on the back edge of it. You know, that little flange that's kind of stamped into this thing. So that's only going to go so far anyway. So we don't have to worry about that. If we want to clean that up a little bit, we can. So we have to get some measurements on this and do the best we can to get a bore diameter. That's the most critical thing. So I think the best way to do that, I would love to use a dial bore gauge. I'm going to try it. All right, so I do have one that'll work. I've actually never used this really small one before. I made some arrows here. There's 3 arrows on spots that are sort of good. You just can't go too deep in, because the further you go in, the more it kind of tapers back because of the corrosion. Run 0 there pretty good. So really all you're doing with this is just a comparator. You're comparing what you're measuring by setting this on 0 to what it mics up when you mic it at 0. That's a plus 1 thou there. And this one is pretty much 0 there. I've got 2 of them at 0, so I think what we'll do is we'll just use that. Okay, so now we'll back it up with a spring gauge measurement too, with a micrometer, but I want to try to be as accurate as possible. I need to have this finish out the exact diameter it's supposed to be. They make holders for these bore gauges, you know, to do this in a little bit more civilized fashion, but being that I'm pretty much uncivilized all the time, we might as well just use the vise on Dad's old bench. That'll be good right there. And the magic number is 1.180. 175 and 5 is 80. So 1.180 imperial is our bore diameter based on this. 1.180. Okay, so we're going to write that down. That's going to be our target for the final bore. I think 30 thou on a side will work fine for this, and I think we got enough meat for that. We got 110 thou on just this one spot right here. Not even consuming a third of that, so I think we'll be okay. You know, maybe a 1 thou press. It's really all we need for something like this with the Loctite. So we're off half, 1, 1.5, 1 3/4 thou or so. I'm going to try just bumping this. May just shim it. This is low, that's high. So let me set it on low 0, and we're high there. Let me just try tapping and see what happens. I don't really want to do that too much on this. I don't have any shims or anything there, but we're going to try it anyway and see what happens. Try to get this nice and true. Doesn't have to be all that tight. There's not going to be a lot of tool load. That's a wee bit better. Sometimes just bumping it a little bit does the trick. That's within a half. I'm going to call that good. If I put, you know, a piece of aluminum or something in here, unless they're exactly the same size, which I don't really have any of that, it's gonna throw everything off. So I'm just going to wing it and go this way. Again, we're not talking about a lot of tool load here. Okay, the depth of that step currently is 540 thou. I'm just going to go up to it right now. We can clean it up later. Yep, good. All right, so I've touched off on the face again. I know how deep I want to go. So let's just take off 20 thou, 10 on the side. Well, the surface finish is nice. See where we're at. But we're nowhere near cleaning it up. You can really see those spots now. Let me see if I can get you in there to do that. You can really see them now. You see that? I want those to clean up all the way if possible. I mean, it's not going to kill us because they'll be behind a bush, but being behind a bush is usually a good thing, but or in front of one for that matter. I'm going to get you back a little bit so I can put the spring gauge in. Let's see how much we took. Okay, 1.202. So our nominal we figured out was 1.180. We took off about 20 thou, which is what we were trying to do. So again, if we took off 60, which would be 30 on a side, that would be about my maximum level of comfort on this. I don't think it's going to clean up with that. I need to slow that feed down a wee bit too. Whoops. Aha! Most of it's cleaned up. Not all of it, but most of it. And we're not too thin over here, I don't think. No, that's not bad. This dimension doesn't mean shit, basically, because we can make our bush to whatever we need to make this. I'm only trying to limit myself to how much I'm going to take out because of this thin spot up in here. 1.225. Okay, so if we add 60 thou to that base number, the final number, 1.80, we got 1.240. We're at 225 now. What is that? 15 thou more. Let's take it out to that. Let's shoot for 1.240. And that'll be our final. 15 thousandths overall. So the way my DRO reads, we need to do 7.5 thou on a side. I'm going to re-zero and do that more accurately. Here we go. I'm going to go in on that shoulder a little bit. And then we'll come in. Maybe we kind of redo that shoulder. Whoops. Sorry. I'm bouncing you guys around like a basketball. We should be at size, and look at that. We're pretty much cleaned up except one little spot there. And there is quite a bit of material over here still. Yeah, so you can see that is really not that bad as far as thickness goes. I mean, it's thin, but not terribly thin. There's going to be a bush in there. But that is the maximum I'd be comfortable with. We should be at 1.240 or very, very close to it. 1.239. So we're pretty much where we need to be. I'm not going to worry about that 1 thou. Push, push in the bush. The depth is 540, but I went to 560. I took 20 out of it, so we don't want to go any more than 560. That'll be in a couple days, though, because I'm going to have to make the bush, install it, and then let it cure for 24 hours at least with that Loctite. I think this is going to solve this. I think we're going to be able to save this. So what we can do here is measure this thin spot. I mean, we know what it's going to be. It's going to be 30 thou smaller because we took 60 out. And that's at 80 thou. It started at 110. So yeah, 30 thou smaller. And it just doesn't look all that much thin, you know, that thinner. So here's the problem. This is a piece of 1.25 inches. It mics up nominally at 1.245, so it's actually 5 thou under. And right now, just taking a few thou off it. 1.242, 1.243. So I don't know if we'll be able to use this. Might just have to bite the weenie. And the next piece I got up is much larger. I hate to waste material, but I think we're just going to end up having to do it. Change in plan. So I'm thinking, why can't we just make this bush out of steel? This is a piece of fork tubing, which is excellent material. And I've machined this stuff before. It's it's readily machinable, and it comes up with a good surface finish depending on speed and feed. Actually about 1.412. And we can get a 1.180 diameter bore out of this. There's enough wall thickness. And of course we can get, excuse me, the 1.240 OD. I think I'm going to do that instead. I'm going to use this material. So we're going to try it at least. And also what it might do is give us a little bit more strength around this thinner area here after it's pressed in. Keeping with the same idea of no more than about a thou crush. So the order of operations here are going to be, we're going to turn it down close. We'll get it within 10 or so. And then we'll switch over to a boring bar and get that close to the 1.180. That way we don't have to take a whole lot out of that bore once it's pushed in. And this stuff's going to, you know, obviously generate a hell of a lot more heat machining than the aluminum would. And of course tool load too. That's another thing we got to consider. Let's get 100 off it. It'll be down about 1.310 and we'll take it from there. Take 60 off it overall. I'm not taking a heavy enough cut with a heavy enough feed to break that chip. And it leaves a decent surface finish so we can also polish in by hand. So that was at 60. Let's go to 100. Well, I'm just roughing it in. Let's bring the feet up. No reason. I'm roughing it in. Not much better. .312. Oh wow, that's 1 in 5/16 exactly. Isn't that cool? So if we decide to take this down to 1.250, which is 10 over, which I think is about right, we got exactly 62 thou to take off. I also extended this a little deeper so we have room for the cutoff tool. Parting tool. Kind of like a parting gift. Bastard. Freaking spaghetti. 1.260 exactly. We'll go 10 more. So let's run her up to 1,000 and slow the feed and see how the surface finish looks. I'm not going to use this insert. This insert's a used insert, so this is a roughing insert right now, but I just want to take a look at that. That's pretty nice. It's a little warm, so it's measuring out at 1.253. Do a spring pass on it and see what it does. .251, good enough. All right, I'm going to leave the aluminum insert in. You know, it's got a high positive rake. Sometimes it works pretty good on this steel. Sometimes it doesn't. Since this is going to be a steel bush with 30 thou walls, I don't think we'd have any problem pushing a steel bush in, especially if we machine a slight lead on the end that's going to go in first. That's at the same size as our 1.240 to get a square. And we can even make it just a skosh long and then face it off so it is exactly parallel, or flush I should say, with this surface right there. And we'll bring it out to 1.170. Do it slow to start off with, see what it does. It's going to be the only problem with this. There's all the chip buildup in there. Take a spring pass. And not terrible. Okay, that was a spring pass. I had to do 10 more, but we are exactly at 1.170. So 10 thou below our finished ID, and we're 10 thousandths above the finished OD. All right, I shall show you what we're going to do now. If you recall, yesterday we weren't too careful about what this end bore was. It really doesn't matter because we're going to make the bush to it. I set the dial bore gauge up to exactly at 1.240. Just like we're measuring a cylinder on an engine, to the right is plus, to the left of 0 would be minus. This gives us an accurate measurement as to what this really is. So we know that this is basically at 1.238 and a couple of tenths. Because like I said, we didn't pay too much attention to the final amount, final size on this. It doesn't matter. And the dial bore gauge, or I should say the snap gauge, whatever this thing is, basically confirms it. Maybe 38 and a couple of tenths. We have parity with the dial bore gauge, so we know exactly what this is. Because we got to nail this. We got to have this right. This is 1.238 to 1.238 and a half. We'll give it a half thou tolerance. We want this to have about a thou crush on it. So if it was at 138 and a half, we want it at 139 and a half. 1.2395. That's where we want this finished size at. This, now that it's cooled down, this is 1.250 and 5 tenths. So that'll be 1.2505. About 5 tenths, maybe 4.5. I don't have the tenths dealio on this one, but I can tell. I've been reading a micrometer long enough. 11 thou to take off. There you go. It touched off and I can hear it singing, so I'm not going to run it too fast. I tried 1,000, I'm going to run it at 800. And we'll slow the feed down just a little bit. Zero the DRO. Try sneak it up on it. This would be about 8.5 thou. Reset back where I was. Now we're right at 240. So that took off. I'm glad I only went 8. Just took off a little bit more. Probably because my touch off may have been heavier than I thought it was. That's usually the variable in that. Now that we've got a cut and I know I'm right back exactly where I was. So 230. Actually, we're like at 240 and a couple of tenths. Really, I just need a thou off of this thing. So we might just take it off with emery. We're so close right now. If we want 239 and a half, you know what I could do is try a spring pass. See what happens. Just not touch anything and see what it does. Not sure I like the look of that. How much it was cutting. Nope, 39 and a half exactly. And it's a little bit warm. So it might shrink just a tiny bit, like a tenth or two, but yeah, 39 and a half. We're going to leave her right there. Just polish it up with some Scotch-Brite. It won't take any material off. Now, when I say it's not going to take any material off, that's a little misleading. It actually might size it down slightly more because when you measure a fresh cut, you're measuring kind of the fuzz and shit that comes off of a cut like that. But we're still at 239 and a half, or very close to it. We were a couple of, yeah, now we're like dead nuts. We were just a skosh above. We were probably 239 and 6.5 tenths. Now we're down to 5, so that's good. Yeah, that looks great. Right now we're going to cut a small lead, bring this diameter down to exactly what it's at on the body right now, which is 538 and a half. That way it'll start straight. All we need is a little bit, 1/16 of an inch or so, just to get it started. So I'm going to do that off camera. We're going to part this with 560 thou plus like 10 thou. Wasn't it Shakespeare that wrote parting is such sweet sorrow. Well, that proves right there that Shakespeare was a machinist. I mean, because I put parting right up there in the same category as a root canal. I'm touched off. This is an 80 thou wide cutter, so we're going to go to 80 first, so we don't screw that part up. Now we're 0 with this edge. So 570 right there. Let's try 600. That's going to be too fast, I can tell you right now. Let's go to 360. Not on steel, it's going to suck with this. That's a brand new parting insert, by the way. I'm not going to take any chances here. There it is. Superfly. Okay, I changed gloves so I wouldn't be cross-contaminating. I want to show you this. That bottom edge is the lead, and I'll show you how it just wants to go in. That's how you do these things. You put a little lead on them. That way they start square. Otherwise, a thin piece like this, you start that sucker off just slightly and it's sayonara to it. So I've got it all cleaned up really well. I buffed this out with a little bit of Scotch-Brite and cleaned it out with brake clean. Deburred everything, chamfered, you know, lightly on it. We're going to put a bigger chamfer on the end of this once we're done. Once it's all together, because we got to accommodate for the radius on the inside of that seal. Because it's a stamped steel piece, but I'll show you that when we get to that point. First thing we're going to do is we're going to get some of this Loctite 638 on the bore itself, smooth it around, smooze it around, schmooze it. I'm going to put it on both sides, the bore and the sleeve. And by the way, I am well aware that the weep hole needs to be re-drilled through a steel bush now. But that shouldn't be any problem with an appropriate sized drill bit. Okie doke. Take one of our pusher tools that we use for water pumps. Actually, you know what? We're going to need something in between there because I think we're down on the stroke. If I did my job right, shouldn't take that much. Yeah, it doesn't. See, I can even just use the I can use the thing without the handle, but we'll put it in anyway. There it is. I don't want to go too far with that. And remember, it is a thin piece. I could fold the edges over, no problem. Because it's sticking up proud about 10, 15 thou. Well, look at that, huh? You zoom up a little bit so you can see a little better. Get my fat hands out of the way. Okay. I love it. And if you're curious at all as to what the size is right now, freshly pressed in, remember our finished diameter is going to be 1.180 or 1.171. So we've got basically 9 thou to come out of that, which is perfect. I was shooting for 10, so I'll take 9. I'm not going to overanalyze it. I don't want to get analysis paralysis here. We're just going to go ahead and finish this up tomorrow. But I thought you might be interested in seeing that. So 150, 60, 71. All right, of course, it's the next day, and that's all ready to go in the lathe, but I have a little analysis paralysis going on. Who would have thunk, huh? But I think I have a cure. I talked to the man himself. Anyway, I'll explain it to you here in a second, really quick. Over at the box bench, whatever you want to call it, and we'll show you the new water pump seal, the mechanical seal, and go over what we discussed on the phone and what my ultimate diameter is going to be on this bore. All right, here's the two components of the mechanical seal. This would be the stationary part that goes inside the body that we're going to press in. And I mentioned before about that blue Loctite seal or whatever the hell they use on that gets activated once it's pressed in. So that's what you see there. And this is the part that goes in the impeller. We don't have to worry about that. Just going to set it over to the side. It's very important not to touch these surfaces, these two surfaces that mate. I forgot what Taz said these are made out of. It's some sort of a carbon ceramic or something. Or that's ceramic and this is carbon, I don't know, kryptonite type thing. Now the question I have though is, as far as this diameter goes, as you saw in the earlier parts of the video, we came up with a 1.180 bore diameter as the nominal on the one that was all chowdered up. As close as we can get, and I'm pretty confident we got an accurate measurement on that. But if we take the new seal and very carefully mic it up, both at the very end, which you would typically think is going to be a little narrower for the purposes of installation, at least getting it started. 1.185. That doesn't sound too terrible with a 1.180 nominal bore diameter. It would be a 2.5 thou crush on each side. And this is only a stamped steel piece, but I kind of overcomplicated this a little bit, sort of. I mean, go figure. I emailed the Tasman himself, easyv65.com, and asked him if he could potentially measure a good bore on an MB4 pump like this. And he said, I'm just in the process of cleaning one up right now. I'll go ahead and do that for you. So he emailed me the measurements. He came up with around 177, 1.177 and a number of tenths. So let's round it off to 1.178 as the nominal bore size. And this is 1.185, and I'm going with 1.180. That would be like a 7 or 8 thousandths crush if I go with his dimension. I think that's too much. I don't think that that's going to fit. I think we'd end up distorting the shit out of this thing. And I told him I was a little concerned about it being too big. And he said, well, what you can also do is back it up with some Honda Bond HT or something. I don't have any Honda Bond in stock, but I do have Yama Bond, which will be fine. And we may end up doing that. Part that I'm in analysis paralyses is what to make that final bore diameter based on what I'm seeing on this seal. Now I mic'd up the old seal too, and the old seal comes closer to the 1.180. It's about 1.183, but of course it's been pressed in already, so that's unreliable. So the question remains, is there some variability between the machining on these water pumps, even if it's an MB0 to an MB0, like a Magna or the early Sabre, or an MB4 pump, which is like on this one here. So I don't know. I'm just going to go with the 1.180, and I'm going to favor the high side of it. So if it goes a little bit big toward 1.180 and 8 tenths or something, I'm not going to be sad about it, because with the size of this thing, it should press in perfectly at that point. And we probably will back up this spot right here where you see the blue there with a little bit of Yama Bond, and then send it and not overcomplicate it any longer. I like accuracy, as you know. I want to be accurate, and I only get one shot at this. You only get one shot of putting the seal in. You got to get it right the first time, and since we're trying something I've never done before, I'm kind of trying to be double, triple, quadruple checking to make sure that my sizes are all going to be good. So let's go over to the part and let's get this thing bored out. I polished the crap out of this thing with some emery and some Scotch-Brite to make it nice and smooth. There is a little low spot in this. Not sure why. Like right there, it just dips down, and could be just from the emery. But that is most definitely true enough. Now, I kind of lied to you yesterday about, well, I made a mistake, about not having any aluminum shims or anything to shim this up and really give this a good crank. I forgot that I had some old pop cans, or in this case it's kombucha cans, so I don't drink beer because I can't drink alcohol. Wish I could, but I can't. But this Dr. D stuff is actually really good. You will be surprised how consistent the thickness of an aluminum pop can or aluminum can of this nature is, as far as when you cut it up and use it for shim stock. And I completely forgot that I had one cut up in my shim drawer over there, so we just put her in and cranked it up good after bumping it around. The reason why I'm mentioning it only is because we're going to be having a little bit more tool load because of that steel instead of aluminum, whatever you want to call it. I say it that way just to kind of screw with you guys across the pond, because it's just one of these things where I joke around a little bit. How come you call it aluminum and you're in the USA? Well, because I'm with people. All right, so let's go ahead and get this get set up and bore this out to finished size. Okay, I remeasured it just for shits and giggles. We are still at 1.171 and a couple of tenths. Our target is 9 thou. We're going to take 9 out of this, and we'll do it in 2 passes. That's good enough. I guess I could use Daikin Blue, but too lazy. I'm going to run 1,000 RPM and a very, very slow feed rate. When we're touched off, we'll hit 0. All right, slight change in order of operations. I forgot one thing. What we're going to do is bring this face down so I can bump off on it and get the depth. Remember, we're a little proud right here. X is fine. I'm not going to worry about that as far as touch off goes. So what I'll do now is we'll just blue this up. Now for that, I'm going to slow it down to 800. Do not need that kind of speed for facing this off. This is going to be hard for you to see because I just can't get in here too well. I'll get some light as best I can. No power feed. Aha, there it is. That's fine. Just touching it. That won't hurt nothing. So we're just touching it. Perfect. Now we know we're right up to it. Set a 0 on the Z. And we may have taken a half thou off of that. Big stinking deal. I'm going to try a different angle here so you can witness the carnage. Since I know where I am on the Z, so we'll just go 560,000 steep on this. I've come back on to 0 on the X, you know, with cross slide. I know I need to go 9 thousandths. Let's go 6, and then we'll take the last. So that's 3 thousandths on the side. So that may have been a little bit of a heavier touch off, so it's probably more like 8, but that's fine. Away we go. Well, that's not bad at all. Just going to use the spring gauge for it, the snap gauge. Boy, I am glad we only took that much. According to this, we're on size 1.180. Again, my touch off, the touch off is always the variable. You know, you think you're only touching off a tiny, tiny bit, and then you end up not. And you go too deep when you take a cut, so that's why I sneak up on it. And with little emery and some Scotch-Brite, it'll probably come out a half a thou more, which is fine with me. Yeah, 1.180 and about 5 tenths. So I'm happy with that. So like I said, it's always, you know, practical or prudent to sneak up on these things before you go for the gusto. Because, you know, it's easy to blow a dimension. I'll leave that one alone. Well, we're closer to 181 now, and that's fine with me. All right, the final operation here is, I'm going to slow down back to 800, and I got the compound set at 45. We're going to do a 45-degree chamfer. Chamfer that they have on this stock, I didn't measure it, but it is quite generous. So we're not going to go quite that much because we don't need to. It is a little risky when you're chamfering a bush like this that is so thin. So we're just going to take it easy, and hopefully we don't catch an edge. So essentially what we've simply done is chamfered the steel bush up to the aluminum. And yes, I am not going to forget to set this up and drill out the weep hole. It's not overcomplication if it works.
Warning. The following section contains technical examination with hypothesis and extrapolation of data for the purposes of examining a measured anomaly. If you do not like this type of content, just kidding.
Alright guys, label this section fun with math, which is probably incorrect, but you know, as far as the mathematics goes, 50-50. But I want to show you something here, and again, I'm not trying to teach you how to do a water pump rebuild in this video. There are other videos that I have that I will link to in the description or put a card here for doing these water pumps or similar water pumps. But this is relevant to what we're doing right now because the objective here is to get this water pump back together to prove out that this repair worked. And I can't quite do it yet because I have an anomaly in regards to a measurement, and I can't put anything together until I resolve that. Now, if you do a mental rewind, you'll recall that I used a depth mic from this surface, you like that sound effect, to the end of this shaft where it was protruding. This is the slot that engages to the oil pump that drives the water pump. And that dimension is very important. That's why I did that, because we do have a problem. Now, when I did that measurement, you may pick it up in the video, but I went, like that, because this is the number that I got. I got 428 thousandths. This is way out of the expected number that I would typically see on these. Now, I haven't done as many as Taz and other people have done, but I've done enough to know, and referencing Taz's paperwork, this number should be around 470 thou plus or minus 25 thou. So even if you subtract a 25 thou from 470, this is way below that. And I'm like, what in the hell is going on, and why would this be to this dimension? It just doesn't make any sense on either an MB4, which is what this pump is, you can tell because it says MB4, or an MB0 like on the Magna. They're all the same pretty much as the stick out goes, very close. Every one of them I've done 3 or 4 and whatever it is so far. This is out of spec as far as I'm concerned, and I needed to verify what's going on in here. The reason this is so important is typically you put the new one in the same depth or the same stick out as the one that came out. This is too far off the norm to do that. So we can kind of do this mathematically. First of all, we can measure very easily from this shoulder, which shoulders up against the block. The bolts pull this right up. We can measure from here to here. And here is proof in living color of that. We can shove this in. That's hitting on that shoulder, and it's still just a little bit away from the 2 bosses that go into the block. You can kind of rock it and touch those. So that shoulder definitely is a good reference point. All right, so establishing that fact, what we do here, excuse me, is that we measure from here, this back edge, to that shoulder because it's a known reference point. Because we need to be able to translate that reference to the block where it goes into the tip of that feature on the oil pump that drives the water pump in order to determine a dimension to see how this thing is going to fall in there, if you get my drift. So, you know, pretty easy to do with a depth mic, and I came up, you know, just like this. And that dimension on this drawing is referenced right here, not to scale, of course. And that dimension is 1.332. All right, so the next thing I did was, which wasn't the easiest thing to do, took the same depth mic and measured from the edge. This would be the engine block, and this is the tip inside there on the oil pump, the tang I should say, that engages with this feature on the water pump. And I got a good accurate measurement after trying it several times with the 1-to-2 adapter on here like you just saw, as far as the rod goes. You said rod. And that is 1.530. So now we know this dimension, we know that dimension. All right, so now what I need to know is I need to know the depth of this slot that engages with the oil pump. This is obviously the one that's going in. We're not reusing this one, so we need to know what this is on the one that's going in. And by the way, I did measure the lengths of both of these, the one that came out, the overall length of the main shaft, and they're within a few thou of each other. Now I can't fit any of my traditional measuring tools in there. Nothing will fit in there, including the dial caliper. But I can use the DRO. It's not just for cutting. You can use it for measuring, depending on whether or not you can keep an indicator in a particular position along a single axis. If you got to move around the indicator, it's an invalid measurement. So what we can do is, in this case, is I just put this end in the chuck of the lathe. And I took that same dial test indicator, put it in a vertical position in a tool holder. And then I can run that up to the edge here, this flat edge of the edge of this shaft, zero the indicator, and then zero the Z-axis, which is the carriage axis on the DRO. And then simply move it in until it comes up to the same zero mark on this particular shaft and this radius. And then make that measurement. And that measurement is 414 thou. So what do we do with all this stuff? So this is the fuzzy math time. We know this, we know this, we know this, and we know that. This is the stick out of the original one. And we're going to use that as our base number to check a few things. So the first thing I do is I take this 1.332, which is this dimension here on the casting, from there to the shoulder. And I'm going to go ahead and add the 428 thou, which is right here, which is the stick out that we measured. So that's 1.332 plus 0.428, which is 1.760. And now I'm going to back out the 0.414, which brings us to the inside of that shaft slot. So 1.760 minus 0.414 is 1.346. So what that represents is, with this thing installed in this body, if it was this new assembly, and we had a 0.428 stick out like we did originally, it represents the distance of what that is from back here, which is where it meets the block, to inside that slot right there, because we've backed out that 414. Okay? So we have that 1.346. So now we take this distance, which we know is from the tip of the drive on the oil pump to the outside of that casting, which references up to here, and we subtract it from that 1.530 from the 1.346. And that gives us a 184 overlap. So in other words, if I move to my second drawing, I can show you that. The overlap, the tang on the oil pump sticking out into that slot would be 184 thousandths, which isn't a whole lot. So I'm thinking to myself, why is it that way? So I redid the calculations with a 470 thousandths stick out, instead of 428 like I showed you up here. And when I redo those numbers and we do the same math, we come down to a stick out, or an overlap, of 0.142 instead of 0.188 or 184. So roughly 40 thou difference. So this would be in there 40 thou. So I know right then and there, based on these numbers, that if we use the 0.470 stick out of this shaft like it's supposed to be, plus or minus 25, we'll just do the 0.470. This thing is going to be still with it'll have 142 thousandths of overlap in there, because we're measuring it from the inside of the slot. That's the number that we calculated into when we backed out this 0.414. We know that that is going to fit inside that slot and not cause an interference issue. So my plan is to do the 470 thou stick out and do it the way it's supposed to be, and the way I have experienced it in the past. So the question is why? Why is it found that way? Well, my guess is that it's migrated. I think that this thing has moved. Where is it? The old one. I think the old one has moved over time. I think it has moved inside that bore. Two reasons for it. The first reason being the number is weird. And the second reason is this did not take a whole lot of force to break loose. Usually when you push these things out, and you got to put a lot of pressure on your press, hydraulic press. I mean, load the crap out of it. I did about 1.5 pumps, 2 pumps to load it up, then hit it with heat. Usually you got to add about a pump more, and then finally when it goes bang. Try to go around as much as possible. Add a little bit more force. And there it goes. And when it goes, you know it. Well, in this particular case, it made a whimper, just went dunk, and then it started to move. I don't think this thing was in very well to start with. It's quite possible the bearing seized up at some point as well, and maybe it spun a little bit. Although I don't see any evidence of that inside this bore where the bearing is pressed into. I'm not sure why. We'll know when we push the new assembly in. If it seems weird, then I might just stop there and give Taz a ring and get a new water pump housing and start over. As long as I don't install the seal, I can push this assembly right back out, no problem. So the other possibility is it was installed incorrectly when it was put together. Now with 180-something thousand overlap, or away from the bottom of this groove here, it would still work. I mean, because if you measure that groove, 414 thou, because the tang, I can't measure the length of the tang, but you have to assume it's pretty close to that. You know, it's still engaging quite a bit. The other consideration, though, whatever it moves out here, it moves in here. And so when this goes in here, and you have this thing pushed either this way or that way, what's going to happen is if it's too far out, it may be too close to the cover. Or if it's too far in, it may be too far away from the cover. And every one of these I've ever done, I've seen it around 470 thou. This is just too far out, this 428. This example up here again is the same thing. That is too far out of spec. If it was like 455 or something, I go, okay, well, you can live with that. No way. And I double, triple checked that number when I took this thing apart and measured that distance. So anyway, I just wanted to cover that and show you how I came to that revelation, and probably my math screwed up, but we're going to do it anyway. We're going to put this shaft in, 470 thou with the stick out. The tool that Taz provides is kind of like a base tool that sits underneath this edge of the carb body. So when you press it in, it only goes so far. I have some made up as well. Probably use one of mine. It's aluminum. And it's already set for 470 thou. So you can't over push it. 472 thousandths. No harm, no foul. And it's a good, strong push in there. So if this thing migrated on its own, assuming the old one was the same, well, I'll tell you what, my farts are worth $1 billion then if that's the case. And I know they ain't. So let's not put any O-ring on it. Let's shove it in and make sure we can engage with that tang in there. And there's no obstructions, which we'll be able to tell pretty quick. Look at that. Perfect. We've got good engagement, good solid engagement with that. Hear that noise? We're not hitting the center at all. We are hitting that edge, that shoulder that this thing registers against the block with and gets pulled in by those two bolts. So there's absolutely no problem with that. Now the only question is going to be is, was it offset further that way? In other words, with a smaller dimension, which was 428 thou, so in other words closer to this, and pushed up that way for any other reason, like to get the impeller to be in its right position. But this is an MB0, an MB4 rather, which is pretty close to an MB0, and Taz has done 1 billion of these, and this is what is in his information for the MB0s on like the Magna Sabre, early Sabre, and these MB4s. You know, being that the shaft is the proper length and everything, I really don't think that's going to be a problem. So the ultimate test is going to be the mechanical seal, which I'm going to do next. And hopefully we can get that pressed in correctly, because I only got one shot at it. And if it doesn't work, then we got to do something else and probably just replace the whole pump. All right, the seal is in, and it went in perfectly. I am really glad that we went with the 180, almost 181, 1.181 really. And I did back it up with some Yamabond. That was something that Taz had mentioned to me on the phone yesterday. He said, if you have any Honda Bond HT, he said, there's no reason you can't back that seal up with it. And I said, well, I got Yamabond, so I'll use that. It is high temp rated. And that's what we're going to use when we seat the other side, the spinny side of the mechanical seal off camera into this into this impeller so we can get the impeller pushed on, which is a tricky operation in itself. Again, I'm not here to show you that in this video, but since this is relevant to the machining work that we just did, I wanted to show it to you. I'm liking it. Feels perfect. You're supposed to spin these around like 20 times each way, he says, to kind of break into two seals dry, two surfaces, so I've already done that, but it feels perfect. Perfecto! Alright folks, here's basically the finished product. I do not have the bolts in, nor do I have the O-ring gasket on the cover, but the cover is cleaned up and ready to go. And we're turning, and no impact with the impeller on the inside cover. Now. I want to be brutally honest with you here. When I first put this together, let me see if I can get these pins out here without them flying everywhere. We did have contact with the inside of the cover here. It was contacting, and you can see a little bit of witness mark around the edge there. And I'm like, what in the hell is going on with that? So I put this whole assembly in the lathe and indicated in the hub of the impeller, and it was running out like, I don't know, 1/8 thou or so, which, you know, this is a stamped steel part. It's not machined. So I'm like, the OD of that, you know, 8 thousandths run out on that shaft, that's perfectly acceptable. So then I looked at it in this perspective, and I could see that the fins were running out. So we had high and low and high and low. And so what had happened was, when I resized this, and I didn't mention this earlier in the video because, again, it's really part of the water pump assembly stuff. When you take these out, when you push these impellers off the shaft, that's after the shaft is all removed, and you know, you have I have a special rig for it made out of aluminum. When you push it through that hole with a hardened pin that's supplied in the V65 kit, you're not supposed to heat these when you take them off. You just push them out. Because you don't want to distort the metal. You don't want to change the metallurgy and distort it so it won't go back on right. So you just push it off. Well, this one was particularly hard to come off, as I mentioned before. So I resized it, which is essentially putting it in a certain fixture that I made for that purpose, and then sandwiching it between two pieces and pressing the shit out of it in the press to kind of flatten it out, because usually it domes in right here at this transition. It's not the center or the shaft that was running out. This thing was sprung, and I should have checked it better before I put it aside and got ready to install it, and I didn't. So this is not a deal breaker. All I did was, I said, well, I'll just bend them, but I need to bend them in a precision manner. So we put them over here. I put this guy in the mill and just ran it around with an indicator to figure out which ones were high. And I got this little pusher tool here, which is what I use to like push things together when I'm doing like fuel joints and fuel tees and things like that. And I just used that once I identified the high spots to push them back down, and then just re-indicated them in. So they're all pretty much within a couple of thou, except one which is a little bit low, but I'm leaving it. It's not going to be a big deal as long as it's not high. So yeah, a little pucker factor on that. It doesn't put any strain really on the bearing. This is pretty, you know, flexible as far as putting pressure on it. You know, I just straightened it out, so it's not going to be a problem. The really interesting part of this is with the stick out it had before on this back side, which was 426 or something like that, this would have been in further. In other words, this impeller would have been higher up, closer to the inside of the cover, and it wasn't hitting before. So again, it's just an error on my part as far as this thing getting sprung, but it is interesting that it would have been closer and it still wasn't hitting at that point. It must have been just thousandths of an inch away. I mean, there is some, I don't know if you want to call it evidence, but it does look a little funky on the inside there, other than the marks right here on the outside, that shiny stuff that I did. So who knows, you know, maybe it migrated toward, you know, the impeller side of it, and like I hypothesized before, I do not know. I'm confident that this spacing between the impeller cover and the impeller itself and the body of the I almost said carburetor, the body of the water pump is appropriate, and this will work just fine. So I got a special treat for you. I pulled my dangly bit out and I'm going to show it to you. I don't get to play with it very much anymore, so this was a good opportunity. So I turned the side camera on, the dangly bit. What do you think I was talking about? And I shoved it in this hole right here. And it turns out I can get a really good shot and a good view at the relationship between the front cover and the impeller blades. So to check out this footage, I went ahead and put the memory card in it just for you guys. So I'm spinning it around manually here, and you can see that the spacing of those blades are pretty even in relationship to the front cover. So I'm not worried about that at all. They look fine. I'm sure this is going to function normally. But it begs the question, how in the hell was it not hitting before? Because right now we have a 470 thou stick out on this back side, which is again what you typically find. So it's going that way further than it was before. Let's see, let's take a look at our notes. The original stick out was 428 thou. So if we're at 472 now, which is what we're at, see, that's almost 30, 40, 50, 60, 70. That's like 44 thou or so, 42, 44 thou, something like that. That's quite a bit of distance. I would say, if you take a look at this footage again, that those blades right now aren't more than about 50 thou away from the inside of this cover. I mean, it may be a little bit less, but maybe a little bit more, I should say. But assuming they weren't, I mean, how in the hell was it not hitting when we know the shaft is the exact same length, because I measured that, and everything is installed, pushed on correctly. And as far as the stick out goes, again, at 428 thou or whatever it was, it would be more that way. It would be more toward the cover, pushing it that way because it's less. It's less from here to here. Now it's more from here to here. So it's more that way.
Now here's the original clip where it was making those squeaking noises. Let's kind of revisit this. Let's slow this one down so it's more audibly clear, because the frequency will be a little bit lower. So I made a huge error in assumption that this was the bearing making the squeaking noise. Absolutely no way. That was the impeller hitting the inside of the cover, and I just didn't realize it at the very beginning of this work when I was taking this thing apart and kind of doing this test.
So yeah, I'm convinced that this is definitely the right dimension to have on the end here, and I'm really glad I did not put it back in the way I found it. And either it was put in incorrectly when it was built in the factory, whenever this component was made, or that bearing's been migrating out. I don't know. So yeah, very interesting, and I pulled my dangly bit out just for you guys because that's how much I love you. Alright guys, so here's another one in the books. I had a lot of fun doing this one, and I hope you enjoyed it and got something out of it. That's the whole reason why I did it. I can certainly afford to buy a rebuilt water pump from Taz, azv65.com. Here's the link also in the description. Don't send them to me, as I've said before. I don't want to rebuild your water pumps. That's not my gig. Send them to him. My understanding from talking to him on the phone, he's got a pretty good supply of MB0s and MB4 water pumps, this being an MB4 on the Sabre V65 and other bikes and so forth. He can help you out on pretty much any of these things, even if it's not a Honda. So get with him. But that's the reason why I did it. I wanted to see if I could. I wanted to see if there was a way that I could basically machine my way out of this problem with that corroded bore and kind of re-engineer the whole thing and get it back into a working form. I have no question that that water pump is going to perform just fine, and I am most definitely going to use it in this bike. And you'll see that in the future when we finally get it running. So yeah, if you want to see more crap like this, you know what you need to do. Like, share, subscribe, ring the bell. You get notified when I put more junk like this up. And as always, thanks for watching. Don't just repair, restore. And we'll catch you on the next video.